Okay, welcome. So what we're going to be getting into today is chapters 13 and 14, which are going to, broadly speaking, cover what we'll be doing on thermodynamics. Now, it turns out both chapters 13 and 14 are oftentimes a class in and of themselves. So we're definitely not going to cover them in that level of depth. Going to cover what we can, kind of the most important things over the course of 3 lectures. But basically that is what it's going to be. So what we'll be doing, I'm gonna go ahead and share the notes. Um what we'll be doing, I guess that's what I do. What we'll be doing is we'll be first talking about temperature and heat. Now, the first thing I want to discuss is temperature. So start there. All right. So think about what you think temperature means for a minute, and then I'll just kind of go ahead and define it. And it's not going to be a super satisfying definition, at least not at the beginning. And the main reason why is that temperature is something that is um directly perceived by the senses. So you walk into a hot room or a cold room, you can kind of just tell that. Like it's just information that your body kind of sends to you about, oh, this is hot, this is too hot, this is too cold, this is just right, whatever. So it's that information that you get directly, and something we just kind of know that, like, you know, you ask someone, is it hot or cold? Well, what you do is you can kind of directly perceive that by putting your skin near it. So that's the basic idea. Now, another way to put it is I'll put this in quotes, it's the hotness or coldness of a system. And again, those are kind of vague terms. Hotness and coldness are not really defined particularly well. When I say of a system, this can be a single object. So you can talk about, like you're heating up a block of metal on for a forge. You can talk about what's the temperature of the metal, but you can also talk about like an ensemble of objects, like a room, in which case you're generally talking about the temperature of the air, but it can be a combination of things. It can just be a single object. Now, another last way to put it is it's the thing we measure with a thermometer. Now, a thermometer, how that works, basically what you have with a thermometer, you have a small bulb of mercury it doesn't necessarily have to be mercury. I can't talk and write. Thermometer. There we go. It doesn't necessarily have to be mercury, but mercury is a common thing to you. And you have a small bulb and then a long, narrow tube that the mercury can go up. Now, the idea with how that works is that when something gets warmer, it expands. When it gets colder, it contracts. So the idea is that the mercury in the bulb warms up, and as it does that, it expands a little bit, and that pushes it further up that column. Okay. Now we'll talk about thermal expansion. That is one of the topics we'll cover this week. Probably not today. Well, definitely not today. But probably on in the next lecture. Now but that's basically what a thermometer is. So it cools down, the mercury contracts, the mercury level in the tube goes down, it heats up, mercury expands, mercury in the tube level goes up. So that's the basic idea behind what's going on there. Now, I also want to talk about the physical basis of temperature, because this is generally what chapter 13 focuses on. And this is the subject. Basically, I learned about this in the class of statistical mechanics. Now, there was a bit more to it than just that, but basically, in the class of statistical mechanics, it's kind of going through the connection between the standard things you can measure about you can measure physically, and something like temperature. And what it turns out is that temperature is, and I'll say directly proportional to directly proportional to the average kinetic energy of the molecules or atoms of a system. Okay. So the idea here, basically the idea is that when we talk about temperature, what we are directly perceiving, we are directly perceiving through our skin, through various other apparatus that can detect temperature. We are directly perceiving the sort of average kinetic energy of all the molecules that make up that system. Now, they won't all have the same kinetic energy, it will be an average. And the way in which that works ends up being somewhat complex because the atoms are bound together into molecules. And when they're doing that, they can do a bunch of different things. Like they can spin, they can vibrate. When you think about a solid, that's a bunch of molecules or atoms bound together that are all kind of vibrating in unison. It's like this cage of springs and masses that are all kind of vibrating together. So that's what's going on when you talk about that. And and there's a lot you can explore with that. And that's like I said, that's sort of the basis of an entire class, which all I'm going to say about it is that kind of concise sentence right there. Proving that is difficult, and exploring the implications, again, like I say, it's another class in and of itself. Just talk about some of the symbols and units of temperature. So the symbol is just a capital T. This also happens to be the symbol for period in physics, but generally we don't deal with these at the same time. So that's no big deal. The units, there are four I'm gonna talk about. The first is the Fahrenheit. This is what you're used to checking when you when you check the temperature outside. The two reference points for Fahrenheit is 32 degrees Fahrenheit. This is water freezing. And then 212 degrees Fahrenheit. This is water boiling. Okay. So the idea behind Fahrenheit, I believe 0 is defined as I don't remember. There are two reference points. I don't remember the two reference points for Fahrenheit, but I believe 0 is defined as the temperature that an equal mass mixture of water, ice, and salt will reach after you kind of throw them all together. So that's the idea behind that. That's just kind of their equilibrium state. I think that's what it was. I don't remember how the Fahrenheit scale got started. I do actually like the Fahrenheit scale, though. It's one of the things I like about it is that it's got a pretty good, the 0 to 100 is a pretty good representation of human experience. So a 0 degree day is a really cold day. There are some colder, but it's a really, really cold day. You get down to 0, it's quite a cold day. 100, you get a lot of days, in the hot places in the summer, you get a lot of days that are above 100. But for the most part, 100 is a pretty reasonable, 100-degree day. It's a hot day, so it's a pretty reasonable scale on the kinds of days that humans can experience. You kind of have a sense of what what a 10-degree day is like. 10-degree day is very cold. 20-degree day, quite cold, but not too bad. 30-degree day, it's cold, but it's not terrible. 40-degree day, okay, is whatever. 50-degree day, it's starting to get warmer. So, and so on and so forth. You can kind of get a sense of like 10-degree increments are readily perceivable, and that 0 to 100 scale works pretty well. The scale that's far more common to use, and some people like it more, is the Celsius scale. Now, for Celsius, 0 degrees Celsius, this is water freezing. And then 100 degrees Celsius, this is water boiling. Now, the difference here is that the range of Celsius temperatures, they go down, they go well down into the negative. Most places in the world will reach negative Celsius at some point. So and fairly routinely. I mean, for a good chunk of the year, particularly here in Idaho, a good chunk of the year, you're below zero degrees Celsius. You're never going to get to 100 degrees Celsius in the in on the world. That's a purely scientific phenomenon, and the idea that it's 0 to 100 on this scale, like the 0 to 100 is nice, but why does the range of water boiling to water freezing, why does that matter in particular? I don't know that it really does. It's not like it's not like having a it's not like having a distance metric where the next highest unit is a multiple of 10. The 0 to 100 doesn't really mean that much and when it comes to Celsius, but some people still like it. Now these are the commonly used temperature scales. When we get into physics, at least for some of the equations, we actually want to use what we call the absolute temperature scales. And these come up in the case where you can have uh basically, it would help to see the data that leads to the establishment of these absolute temperature scales. But the main thing to think about is that you come up with a lot of these physical laws that where something seems to be dependent on temperature, but basically not in a purely direct way, in a linear way, but not in a purely direct way. Using these absolute temperature scales makes the thing direct. More concisely is that you have physics equations that involve temperature, and if temperature is in the denominator, then you can't use this offset scale because you can't have these divisions by 0. So the two absolute temperature scales, the first one is Kelvin, symbol is K, and your temperature Kelvin, that's Celsius. Your temperature Kelvin is equal to the temperature you have in Celsius plus 273. Okay, I think it's 273.15, but we'll just use 273. So basically, you have the situation where if your T Kelvin is equal to 0, this is what we call absolute 0. And absolute 0 it's not something we can really get to, but it's a theoretical limit where all that kinetic energy I was talking about, where all that stops, where basically there is no kinetic energy associated with the atoms and molecules of the system. And therefore, to be any colder wouldn't have any meaning. Like you can only have 0 kinetic energy of those atoms before there's just 0 kinetic energy, and that's it. So that's what's going on with the excuse me, with the Kelvin scale. The other scale is Rankine. We're not going to talk about Rankine much. We're not going to use it. Kelvin will use, Celsius will use. We won't even use Fahrenheit that much. But it's the same idea. Your temperature in Rankine is your Fahrenheit temperature, plus 459, like 458.6, I think. But again, in this case, your TR, if TR is equal to 0, again, this is an absolute 0. Okay. So basically, these are both scales that use the same degree increments. So you go up by 10 degrees Celsius, you've also gone up by 10 degrees Kelvin. Now the difference there is that, excuse me. The difference there is that is just where the 0 point is. All right. The formula for Celsius to Fahrenheit, this is something that's worth knowing. Your Celsius temperature is equal to your 5/9 times your Fahrenheit temperature minus 32. Okay. So that's one way you can remember it. So that is worth keeping in mind. All right. 1 second, sorry. Right. Okay. Yeah, that's correct. Okay. Sometimes I misremember the fraction. That's why I was checking. All right. So what to discuss next? Well, I think that oh yeah, T versus delta T. Now, the thing to remember here is that this is relevant depending on what your formula has. Like some of the formulas only involve delta T, basically a difference in two temperatures. Some of the formulas involve the absolute temperature. We'll cover some with both. Really one that has absolute temperature, but you got to make sure you use Kelvin for that one. So if you have the main thing is that we know our Kelvin is not equal to our Celsius temperature, but because T Kelvin is equal to T Celsius plus 273, what we can say is we can say that our delta T in Kelvin will equal our delta T in Celsius. And the reason why here is if we do T1 in Kelvin minus T2 in Kelvin, basically what this is going to be equal to, this is going to be equal to T1 in Celsius plus 273 minus T2 in Celsius plus 273. Okay. So you do those, and this is just going to be our delta T of Kelvin right there. And then here you'll have T1 plus 273 minus T2 Celsius minus 273. And notice these two things just cancel out. The 273s just cancel out. So you end up with your delta T Kelvin is equal to your delta T in Celsius. So if you're dealing with situations where, I already said this kind of, but just to reiterate, if you're dealing with situations where it says, where it's saying, you have a change of 15 degrees Celsius, you definitely don't want to add 273 to that, okay? Because that's not what you do. The changes are not 273 more. It's just that those two absolute temperatures would be 273 more. But when you find the change, that shift of 273 takes it away. So it's really important that you don't just blindly add that 273 onto a Celsius whenever you see it. Okay. So just worth keeping in mind. Okay. Next thing I want to talk about is going to be heat and thermal energy. So sometimes, if you've heard this term thermal energy before, you've certainly heard of heat before. But if you've heard of thermal energy before, you might just think that's a kind of a fancy way of saying heat. And for a lot of people, that's how they'll take it. And colloquially, that's fine. The Another name for thermal energy is internal energy. Depending on the situation, you either can be used. Now, the thermal energy, this is why it's called the internal energy. Basically, what this is just the combined internal kinetic energy of the system's atoms, what's going on here? There we go. Of the system's atoms or molecules. Okay. So that's what we mean by thermal energy. The symbol you'll see here is usually just U subthermal. So that U gets a lot of times that gets used to just kind of mean a general form of energy. We use that for potential energies as well. Also gets used for thermal energies. Now, the symbol for heat Heat is a little bit different. It means something a little bit different. And the symbol we end up using is going to be Q. So H was a possible thing, but it turns out that the H was already used for a symbol in chemistry. It's used for the symbol. It's the symbol for enthalpy. I don't know why they had entropy, energy, and enthalpy. I don't know why they used all those terms. Someone probably thought it was a good idea, but in any event, heat needed something different. Okay. Now, heat is different in that really what heat represents, it represents a flow of energy. Okay. So heat and heat flow, that's a redundant phrase in physics. You don't, nobody's really going to nitpick you if you talk about, oh, there's a lot of heat in this room. But in terms of physics, that sentence doesn't really make sense. What you would say is there's a lot of thermal energy in this room, or a lot of internal energy in this room. If some of that internal energy leaves, you would say heat left the room. So heat flowed out of the room. If the room gets warmer, heat flowed into the room and increased the thermal energy. If heat leaves the room, then that decreases the thermal energy. Okay. So basically what we mean by heat here is we mean a transfer of energy that raises or lowers the internal energy. Okay, that is what we're talking about when we're talking about heat. So it really does represent a transfer. Now there are many different ways heat can be transferred. So ways to transfer heat. The first way, and one we've kind of talked about, is we can have mechanical energy go to heat. And basically when mechanical energy gets turned into heat, basically that heat will flow into a variety of systems. Sometimes it's a system under consideration, but a lot of times it will leave that system and flow into the surroundings. So if you think about when you have friction generating heat at the surfaces, if you're just looking at, say, a block, excuse me, some of that energy will flow into the block, but some of it will also flow into the table, some of it will flow into the air, so on and so forth. So mechanical energy can be converted to heat. Generally, it's through friction or drag. And once that happens, where the heat will go, that's another study of something called heat transfer. By the way, this is getting into more of the chapter 14 content, but I want to cover it first because it's relevant to the lab this week. So through friction or drag. Another common way is just heat will flow from high to low temperature. Just kind of spontaneously, okay? And this is all something we've experienced. You have a hot a warm house. If you turn off the heater, then all that heat will kind of leave the house until it's the same temperature as outside. Alternatively, a cool house, it could be hotter outside. You turn off the air conditioning, all the heat flows into the house. Okay. So that's just a it's kind of spontaneous way that heat travels given differences of temperature. You can also have chemical energy be converted into heat. So if you are remembering, or if you took chemistry, um this is in chemical reactions. Now, some of them you have chemical energy that gets converted into heat. And this, as a reminder, is called an exothermic reaction. So basically, you have a bunch of chemical energy in the system. Heat gets released as a result of that system, or as a result of that chemical reaction. That's exothermic. Alternatively, you can have a chemical reaction that requires an input of heat from the outside. And in that case, what you need, that would be kind of an endothermic reaction. Now, there are certain situations where you need a certain amount of the system needs a certain amount of internal energy to activate. We call that the activation energy. So it needs to be at a certain temperature, but it might still be an exothermic reaction. So a good example of this is like burning of wood, where wood it won't just spontaneously react with air and release all this energy exothermically. But if you get it high, if you get the temperature high enough and you have wood and air together, or wood and oxygen together, then they will undergo the exothermic combustion reaction. So that's just kind of a sidebar into chemistry, but the idea is that these ideas are quite related. So this is one of the ways that physics and chemistry really do touch on one another. So in any event, the main one we're going to look at eventually is we're going to look at from high T to low T. Well, that's not entirely true. We'll also be looking at this one kind of today, but really just to kind of describe sort of some of the equations that we want to talk about. And really, it was this connection of mechanical energy to heat that a guy named James Joule, he discovered this. And I'm going to show you this setup here. So hopefully this will work. There it is. All right. So this is James Joule's setup. And the idea here is that what he did here is if you have, you have a, some height that this thing and you have some mass m right there. Well, the gravitational potential energy is just mgh. Well, the idea here is that if we were to drop this weight, it would pull on the string, it would pull on this drum and kind of and twist it. And basically what that would do is that would turn this paddle wheel inside the water, and it would impart kinetic energy to the water. Well, James Joule's idea was that, well, once that water more or less gets back to still, that kinetic energy will have been transferred to the internal energy of the water molecules. And what that means is we should be able to observe a change in the temperature as this, when we from adding this mechanical energy. And sure enough, he was right. And the thing is, this is easy to calculate. So you can very easily calculate the potential energy. And his idea here was, okay, that this U sub G, basically it is converted to heat and it goes into the water. Okay. So that's what he was saying. And once that happens, then basically your thermal energy goes up, and this will be observed in the rising temperature. Okay. So this idea is that James Joule investigated. He was talking about the heat capacity of a system. Okay. And the idea here is that we're talking about heat capacity. We're talking about the energy. Whoops. The energy required to, actually, I'll say heat, because heat is an energy flow, but the heat required to raise a system 1 degree Celsius or Kelvin. Okay. So, and then remember, raising it 1 degree Celsius is the same as raising it 1 degree Kelvin. So the idea here is that you have Q, and then the symbol we use for heat capacity is a capital C, and then your change in temperature. So if your change in temperature is 1, then your heat capacity is just equal to the heat that was required to do that. Okay, so that's what's going on here. So again, this is heat. This is heat capacity. And this is change in temperature. Okay, so the issue with this is that heat capacity is actually a function of multiple things. The first thing it's a function of is the size of the system. And you can imagine this, that, you've got a pot of water that you're boiling because you want to make pasta or whatever. You're boiling that on the stove. the stove. And you can imagine, well, that you can quantify, it might be difficult, but you could in theory quantify how much energy you need to put into that water to boil that pot of water. Well, if you put that same amount of energy into a pool of water, it certainly wouldn't boil. It might not even do anything to it. So the amount or mass of water is one thing that heat capacity depends on. So if we think about this, C depends on really two things. One is the mass of the system, okay? But the other thing, it depends on the material of the system, and different materials can absorb heat with more or less effect. Now, the idea is that heat in general does cause, heat in general does cause the temperature to rise. You can't just add heat to something infinitely and not have the temperature raise. But different systems require more heat to raise them the same amount, or different materials require more heat to raise them the same amount, even if the masses are the same. A good example of this, you have 1 kilogram of water and 1 kilogram of aluminum. Way easier to raise the temperature of aluminum. Aluminum changes its temperature very, very easily, and it does not require much heat flow in or much heat flow in to raise it, or much heat flow out to lower it, okay? So really, this equation that I've given here, this heat capacity equation, it gets boiled down to something that's a little bit more that isolates these ideas a bit more, and that is this equation. So this next equation is called the specific heat equation. And what this equation is saying is it's saying, okay, our heat is this, and it's still going to be proportional to your change in temperature, but we're going to break that heat capacity into two things. So basically, we say that heat capacity was equal to the mass of the system, and then some property of the material. And this is often indicated with just a small c. The subscript P stands for at constant pressure, which I'm not going to go into. That gets to be relevant when you start doing more analysis of heat flow into gases, which I don't think we're really going to do. But in any event, the idea is that this specific heat equation then looks like this. Okay. And where I'll try and make it a little clearer, that's a lowercase c. But what you have here is, again, Q is still just heat. Delta T, this is change in temp. M is the mass. And then C sub P is what we call the specific heat of the material. And the idea is that the specific heat of the material, it's unique to, it's kind of like a material's density. It's unique to a particular material. And basically it's measured in, the units are joules. So joules are in the numerator because the units of heat are just joules. And then the units of mass is kilograms. So that means it needs to have a kilogram in the denominator there. So the kilograms in C sub P cancels with the kilograms in mass. And then it also needs to have a Kelvin, or it could also be, and this is more common, the way to see it, degrees Celsius down here. So they are, in fact, the same thing because that temperature is a delta T. Okay. So the strictly speaking with Kelvin is correct because Kelvin is the SI unit. But if you're dealing with deltas, the thing to remember is that there's no difference between Celsius and Kelvin. When you're not dealing with deltas, then you need to be careful. But since this specific heat equation does only care about changes, then we're good. We don't really need to worry about that. Okay, so hopefully that gives you that kind of gives you a sense of what you need to do to use in order to use the specific heat equation. Just one other thing, C sub P, these you look up in a table, with one exception, and you can look this one up in a table. But the way I tend to do it is I would say C sub W is the specific heat of water. This is one that I remember because it does come up a lot. So maybe the people that deal with the chemists that were dealing with specific heat of water, maybe they had something to that. But the idea here is that this is 4,186 joules per Kelvin or kilogram Kelvin. Okay. Specific should have been specific heat of water, but okay. Now turns out this is equal to 1 kilocalorie. Or 1,000 little c calories. Now, when you are reading the calorie figures on in food, they're talking about kilocalories, not little c calories. So these are the cal in food. These kilocalories. So that's 4,186 joules of chemical energy per kilocalorie. Okay. So you can imagine that this like that's that would be lifting a 41 kilogram object 10 meters, and that's 41 kilogram object, that's a pretty heavy thing. So the idea is that yeah, their chemical energy is pretty dense in food. Now, the reason why this unit of kilocalorie came up is this was how, and this comes up in chemistry investigations, and we're going to be doing the lab kind of covers this a little bit. But the idea that what people would do, I'll try and draw a diagram of this, is they would do, so I'll just have and this will be the chemical reaction. And they would have some chemical reaction, and it would be filled, it would be in this container full of water of known mass. So water of known mass. And the idea is that there's not a really convenient way of measuring the energy released from chemical reactions. But if you know how heat changes the temperature of water, you can use the change of temperature in water to infer how much energy was released from the chemical reaction. So if energy is leaving this chemical reaction, Q is going into the water. Well, what we should see is if we've got a thermometer in here, and it is filled with mercury, or some of them use bromine as well. I think really what you want is you want something that is liquid at room temperature. So and generally is not too highly reactive or interactive with the glass. So basically the idea is that your temperature will go up. Okay, so you can use, the idea then is you use delta T to find Q. Okay. And this is something that can be done. It's going to be something similar to what we'll be doing in lab on this week. Now, we're not going to be doing a chemical reaction. What we're going to be doing is we're going to be using resistive heating from an electrical resistor. So you might have a better idea how to find the energy dissipated by a resistor. And we're going to be seeing, okay, how much does that raise the temperature in this of this container of water. Now, the main thing to know is that what you really want is you want to make sure that there's no heat leaving this thing. Okay. And because because if heat leaves, then that causes the temperature to go down. And in which case you haven't accounted for the difference between the heat added to the water and the heat left the water. Okay. So that's something that could be an error. So basically these containers, they're called calorimeters. They have to be insulated well so that no heat leaves the system as well. Okay, but I think that's just about it for what I wanted to cover today. So I'm going to go ahead and end things there. So thank you for joining me today, and I will see you in the next lecture.